Thank you for whoever's managed to make it back. Very kind of you. And those who haven't managed to make it back, they're just going to miss out on the candy and the stickers that I have around. So the plan is we will try to keep on time as much as we can. And if you ask questions, you win yourself a candy and a sticker. I will throw the candy to you. The sticker you can pick up and on your way out. And with that, I'll just quickly hand over to Nilanjandev, who will be our first speaker, speaking about primordial black holes and the stochastic gravitational wave background as a probe of non-standard reheating history.
So let me thank the organizers for giving me the opportunity for presenting here. I shall be mainly focusing on primordial black holes and stochastic gravitational wave background to probe the thermal history between the end of inflation and the start of Big Bang nucleosynthesis. So let me start with this diagram of. So let me start with the diagram that shows the cosmic history. Here in the right hand side is present day time, and here we have the Big Bang singularity. And here you can see that this is cosmic microwave background from where we get the earliest observable signal today. So any era before cosmic microwave background that cannot be directly probed. But between cosmic microwave background and inflation, basically the earliest phase after Big Bang nucleosynthesis, the accelerated expansion phase, there is BBN or Big Bang nucleosynthesis when the neutron and proton forms the helium ion. During BBN, the BBN models constrain the constituents of the universe quite strongly. So we know what is the expansion history from cosmic microwave background to the Big Bang nucleosynthesis. But from the end of inflation to the start of BBN, this era remains still now unresolved. Now the time has come for the gravitational waves. With the advent of different gravitational wave detectors, we have the opportunity to probe the early universe through the cosmic gravitational wave backgrounds. But even in that scenario, we need to understand the gravitational wave signature that is being moderated due to any non-standard reheating history or non-standard expansion phase between these two events. So I shall be focusing on mainly three different directions. In first scenario, I shall be considering primordial black holes formation being affected by the presence of a non-standard reheating history. It can happen that PBHs are forming during reheating phase. It can also happen that PBHs form after the reheating phase, and I will show that in both the cases, the corresponding stochastic GW background will be affected due to the presence of the reheating phase. Then we shall consider a very specific scenario where primordial black holes are basically constituting the reheating itself. So if we consider ultra-low mass primordial black holes, they can dominate the universe and lead to an effective reheating scenario. And in the third scenario, that is basically the mix of these two scenarios, here primordial black holes form during the reheating phase and then it dominates. So let me start with the first one, where primordial black holes do not form during reheating, but there is a reheating phase and that affects the primordial black hole formation. To understand how this works out, I would be taking a sample model for inflation. This is a popular model known as ultrafluoral inflation. Here I have an inflection point in the inflationary potential determined by these inflection point conditions. So near the inflection point, the potential is flat. So inflation field slows down and leads to an amplification in the two-point function of scalar curvature perturbation. Corresponding to these amplifications in the scalar curvature perturbation, which follows from the solving the Mohanty equation for the co-moving curvature perturbation R, we basically get primordial black holes formed in different mass ranges. And whenever the primordial black holes are forming due to the amplified scalar curvature perturbation, that amplified scalar curvature perturbation also shows the tensor perturbation at second order, and that leads to an amplification in the second order GW background. So the peak frequency of the GW background would correspond to the inverse of the mass of the primordial black holes. That is the standard setup. Now we are coming to how reheating history can affect this kind of scenario. Here we consider a reheating phase just before the primordial black hole forms. So primordial black holes are not forming during the reheating phase. Primordial black holes are forming during the radiation phase, but before the radiation phase, there is a reheating phase. In such a scenario, what we see is that the inflationary energy scales get remapped, and also the end of inflation scale or the moving horizon size during inflation gets remapped. We basically denote this reheating phase, we basically model this reheating phase with the simple equation of state W reheating and equal duration N reheating. In such a scenario, we can denote the remapping of scales like this. That leads to a shift in the peak of the primordial scalar power spectrum. That shift also reflects in the shift in the mass range for primordial black holes, and also the abundance changes. You can see that the black one is corresponding to the instantaneous reheating phase, where radiation starts just after the inflation ends. Orange one corresponds to the early matter domination in between the radiation and inflation, and the orange one has quite a larger abundance than the black one. Now that is the effect on the primordial black hole formation. How does it change the stochastic GW background? In the case of stochastic GW background, the effects are twofold. First, it comes from the remapping of scales that I just mentioned, and the second one comes due to the non-trivial evolution of first order scalar perturbation during the reheating phase. That is encoded by this kernel term, and let me directly go to the result. You can see that this non-trivial evolution of the curvature perturbation during the reheating phase, particularly if we consider a matter-dominated reheating phase, actually leads to an additional amplification in the very high frequency near the end of inflation scales. So here you can see a shift of frequency in the primary peak. That shift corresponds to the remapping of scales that I just mentioned, and then there is a secondary amplification that comes due to this effect in the kernel term coming from the non-trivial evolution of the first order scalar perturbation. One interesting thing to note is that the kernel term here, which leads to the second order GW background, has contribution both from the amplitude of the scalar perturbation and also a time derivative of the scalar perturbation. So thus what we can see is that even if primordial black holes are not forming during reheating, if there is a reheating phase, both primordial black hole formation and the SGWB are affected. Now let me come to the second scenario where primordial black holes are actually forming during the reheating phase. This scenario is not actually very well studied scenario, because most of the analytical and numerical works that has been extensive for the primordial black hole formation during radiation domination has not been so extensive for the case when primordial black hole are forming during reheating. We follow an analytical formalism from this paper. Here we can see that there are changes mainly in two aspects. The mass of the primordial black hole is changing because the efficiency factor gamma is changing, which denotes that how quickly perturbation collapses to form primordial black hole after the amplified perturbation re-enters the horizon. And then the abundance of the primordial black hole is also changing, mainly through the threshold of density perturbation known as critical density contrast. So critical density contrast changes according to the equation of state, and that leads to a different abundance of primordial black hole if we consider different reheating histories. Yeah, this expression is not valid for W is equal to 0. I should have mentioned this expression is only valid for, I think, W is equal to 0.05 something that value, and it goes up to, it is tested with numerical code up to 0.8 or something like that. The analytical expression is in principle valid up to the kination, but when it is compared with the numerical data, the numerical results are only up to W is equal to 0.8. So this validity is like that. This is not at all valid for a matter domination. this particular formalism. So, and this has also been discussed by Sriram in the first 2 days. You can also check his lectures for more details. Now, as I mentioned that the mass changes and also the abundance changes if we have different reheating histories. So, W domination with here we are considering 6 different values of W. This is the radiation. This is W is equal to 0.1, and then there are other 4 values of W that we considered. For a given power spectrum, we see that for different W, we are having primordial black holes in different mass ranges, and the abundance of the primordial black hole is lowest when we consider radiation domination. That is the primordial black hole side. Now let me come back to the side of the stochastic GW background. In stochastic GW background, as I mentioned, there is a kernel term that reflects the evolution of scalar curvature perturbation after inflation. When we consider primordial black holes forming during reheating, stochastic GW background is also basically generated during reheating. The kernel term is very different, so that has one effect. The other effect is how the GW energy density is evaluating after the GW is being generated. If there is a reheating phase after the primordial black hole generation, then that effect is also there. And if we combine these 2 effects, we shall basically get a plot like this. You can see that for different W values, for a same scalar curvature power spectrum, we get different shape for the second order GW background. Now, if we consider a broken power law power spectrum with a peak in a particular region, as you can also see in the right hand side, this power spectrum would be able to explain the NANO-Grav data. We search the parameter space to understand that what values of W and what values of primordial black hole mass are most consistent. What we should mention is that though there is a slope, we are parameterizing the slope, descending slope of the scalar power spectrum, that slope is not contributing very much to the NANO-Grav observable, so it's nearly flat. We can leave that parameter. And finally, we are also fixing the primordial black hole abundance up to its maximum allowed value. So finally, we are left with 2 parameters, W reheating and the mass of the primordial black hole. And you can see that depending on the mass of the primordial black hole, there is a particular value of WRE, typically which is greater than 1/3. That can explain the NANO-Grav data better than the radiation. And also this model is favored if we compare this model with the Bayesian analysis with that comes the model that comes from the supermassive black hole binary. So next I will switch to the second scenario that I mentioned. Here primordial black holes are constituting the reheating history. You can see in the right hand side here the primordial black hole fraction for dark matter is constant differently for different masses. These primordial black holes are little bit higher mass primordial black holes, and they actually survive until today. So they are dark matter candidates. But if we consider primordial black holes in this mass range, which are little bit smaller mass range than this one, these primordial black holes will evaporate by today. So they are not dark matter candidates. But even these primordial black holes are constant because of their evaporation signatures in galactic and extragalactic gamma ray background, CMB and BBN. But now, if we consider primordial black holes with mass less than 10⁸ gram, these primordial black holes evaporate even before Big Bang nucleosynthesis. And thus, they can actually dominate the universe for a short duration before the BBN happens. And we shall get a timeline like this. Inflation ends, radiation domination starts, primordial black hole forms during radiation domination at moving time tau f. This radiation domination we call early radiation domination. This early radiation domination lasts up to the time when primordial black hole dominates at tau is equal to tau m. Then after some time primordial black hole evaporates and the standard radiation domination starts. One interesting feature about this particular scenario is the generation of isocurvature perturbation. When primordial black holes are forming in the radiation domination, the radiation fluid is being converted to non-relativistic dust fluid. That leads to an isocurvature perturbation. If we consider Poissonian distribution of primordial black holes, we can basically express the power spectrum of primordial black hole density fluctuation with a formula like this. We can also take a cutoff of this density fluctuation at k UV. Then when at the time of primordial black hole evaporation, we consider the total adiabatic perturbation, we see that the adiabatic perturbation now can have two contributions, one coming from the inflation and another one coming from the isocurvature perturbation, which has contributed to adiabatic perturbation throughout the primordial black hole domination and then primordial black hole evaporation. As these two components are decoupled, uncorrelated, we can basically simply add these two contributions in the power spectrum level, and that leads to a doubly peaked structure of the stochastic gravitational wave background. Here, each of the colored curve represents a particular set of parameters for mass of the primordial black hole and the initial abundance. We also consider two different spins. One is non-spinning, another one is spinning primordial black holes, actually extremely spinning primordial black holes with the dashed lines. And you can see for each of the parameters, for each of the parameter set, the IISGWB spectrum has two peaks. The first peak comes from the inflationary adiabatic peak, which we model with the nearly flat power spectrum that is consistent with the CMB data, and we also take the cutoff of this power spectrum at the scale where a primordial black hole dominates, because all the modes which are entering the horizon before the primordial black hole dominate will be suppressed in terms of the scalar perturbations. And where the first peak is coming from the inflationary adiabatic perturbation, the second peak is coming directly from the PBH density fluctuation. And you can also see that there are certain scenarios where the gravitational wave detector can actually detect both these peaks. And when both these peaks can be detected, that would constitute a perfect test for this kind of scenario. We also compare our numerical result with the approximate analytical result that we find. They are nearly matching. So we are using the approximate analytical result to also scan the parameter space. Here, there are, you can see that there are three lines. First line is coming from the Big Bang nucleosynthesis. Here, the stochastic GW background is constant from the extra relativistic degrees of freedom during Big Bang nucleosynthesis. This is also known as delta N effective bound. Then there is a nonlinearity bound. This nonlinearity bound is coming because the first order scalar perturbation becomes nonlinear if the PBH domination lasts for very long. So, and then there is also another bound that is in the bottom. So, parameter space below this line, primordial black holes are evaporated before they can dominate. So, if we exclude all these three regions, we are still left with the middle portion where primordial black holes can lead to doubly peaked SCWB. We also calculate the signal to noise ratio for these two peaks. The left leading lines here corresponds to the first peak, the detectability of first peak. If we set the FNR greater than or equal to 10 for different GW observatories like LIGO, ION, AGE, MURESH, ET, so on. The right leading lines corresponds to the second peak, that is the PBH density fluctuation peak. And you can see that there is a large region where both these left leaning and right leaning lines are superimposing on each other. So that is the region where both these peaks can be simultaneously detected. So, so far we have not considered any particular formation mechanism for primordial black holes when we considered the GW background earlier. But now we can also consider a particular mechanism for primordial black hole formation with a broken power power spectrum coming from inflation. And if we consider that, we can basically use that to explain the NANO-Grav signal for the inflationary adiabatic peak. And our parameter space search shows that for primordial black hole forming with a mass like around 10 to the power 8 solar mass and abundance of around 10 to the power minus 10. And also another interesting factor is the slope of the scalar curvature power spectrum. If we fix these three parameters, we can basically explain the NANO-Grav data better than the supermassive black hole binary model does. So that is the third scenario that, and now I'm coming to the next scenario where primordial black holes are not forming during early radiation domination, but primordial black holes are forming during a reheating phase. So primordial black holes form during reheating because after inflation, the reheating phase or inflaton domination starts. The primordial black holes are basically goes on, the primordial black hole forms during reheating and the primordial black hole dominates until the primordial black hole evaporation at radiation. In this scenario, the changes are mainly threefold. First, how the primordial black hole perturbation evolves during the reheating phase. That depends on the equation of state during reheating, W, through the Massageras equation. And so final adiabatic contribution depends on W. Then how the moving horizon size changes during matter domination, primordial black hole formation, and the mean separation between the primordial black hole, that also changes and depends on W. And thirdly, the subtraction on the scalar perturbation during the transition from W domination to primordial black hole domination, that also changes if we have a different W. So finally we get this kind of plot where you can see that if we have radiation domination, that is the solid line, we have a certain shape of the SGW spectrum. But now if we have a little bit slightly different values of W, that leads to different shapes for the SGWB and also percentage. I am changing because any large changes in the equation of state would lead really large changes in the SGWB. Now, as it turns out that we could claim that whenever we could detect both the peaks, we understand the reheating history between the end of inflation and BBN if the primordial black hole domination is there. But recently, what we have seen is that the semi-classical approximation, familiar approximation for Hawking radiation is being questioned. And when we consider the memory burden effect to take into account after a certain period in Hawking radiation, then there is extra two parameters, Q and N, that also comes into picture. And as you can see in the right-hand side plot, the effect of changing Q and N or the memory burden effect of Hawking radiation also have similar effect what we get for non-standard reheating history. So initially in this work, it has been pointed out that ultra-low mass primordial black hole domination can work as a vective probe for memory burden effect. But then we found this degeneracy in our recent work, and we see that the second peak or the PBH PBH density fluctuation peak is identical for memory burden effect and non-standard reheating history or suitable parameters. Only the first peak, that is the peak coming from the inflationary adiabatic perturbation, can break the degeneracy. So with that, I will just leave with the summary slide.
Yeah, hi. So, yeah, one quick question. So, do you have any early thoughts on or how we can distinguish between those two cases where the degeneracy is back? And the second question is that...
No, those two cases of which two cases?
So you showed these two plots, right? So, yeah. So
you mean
how
these
do
two?
Yeah. How do you distinguish between the left case and...
Actually, these two plots are already different because we did not use exactly identical parameter set to reproduce the degeneracy. You can see that in this plot particularly, here the dashed line is when we approximate Hawking radiation semi-classically, similar approximation. That is the dashed line. So here we have RD plus semi-classical approximation. Now, as we deviate from RD, if we take a reheating phase, then we are basically having the blue line. And then if we stay with the RD, but we are changing the parameters of the memory button, we are having the red line. Okay, these two solid lines. You can see for the second peak, that is the high frequency peak or the PBH density fluctuation peak, these are almost identical. Right. Yeah. Even taking into account the non-trivial suppression that comes during.
And just a follow-up question is that I see some enhancement because of this memory button effect. What do you attribute it to?
Yeah, that happens because as you can see here, the memory button effect kicks in when the mass of the primordial black hole is less than a certain value. That means it basically slows down the black hole evaporation. That means you have a larger PBH domination duration, and whenever the matter domination duration is longer, we have a amplification in the ACWB.
Can you go to this 9 number slide? So actually you just, okay, so the second peak actually appears due to this cos term of the kernel. Is there is any physical reason behind of this at the second? Yeah.
Yeah, as I said, in the second order GW background, the tensor perturbation is sourced by the scalar perturbation at the time of primordial black hole formation. Here the primordial black hole is forming after a reheating phase. The inflationary perturbation which was generated during inflation is going through that phase. Now, if that phase is matter domination, during matter domination, the first order scalar perturbation is nearly constant. And just at the start of the radiation domination, this first order scalar perturbation starts to come down and oscillate with a large frequency. And the amplitude is also quite large compared to the modes that is re-entering at the time of primordial black hole, at the time of the radiation starts. So in the kernel term, you have both the time derivative of the scalar perturbation and the amplitude of the scalar perturbation. Here, the second amplification is mainly coming due to the contribution from the time derivative part. Because the modes that are entering during early matter domination has a larger frequency compared to the modes that are entering at the start of radiation domination. Actually, you can see it better from here. So here we are comparing three modes. The blue mode is the mode that is entering during early matter domination. The black mode is entering just at the start of radiation domination. And then the red mode is there that is entering during the radiation domination. And you see that the blue mode, that is, though it is a sub-horizon mode, it is staying nearly constant during matter domination, starts to oscillate with quite a large amplitude at the start of radiation domination. So it is this oscillation that contributes to the amplification in the ACWB.
Thank you, Nilanjan, for the excellent talk. In the interest of time, we'll move on, but please do remember,